Welcome back, Physical Science 20. So this is the FC1 synthesis and decomposition reactions section. So we'll look at observing and analyzing synthesis and decomposition reactions, represent them using manipulative skeleton equations, balancing equations, etc. Predict the products of synthesis and decomposition reactions. So that's a key thing, looking at what is produced and describing how some of these things affect the environment. So if you look over here, the reaction, the figures below are examples of synthesis reactions. So over here, if you can see it, solid sodium in the presence of chlorine gas. So the sodium and chlorine come together to make solid table salt. And the interesting thing here is solid sodium is very reactive. Chlorine gas, of course, is dangerous. But if we put them together, we get table salt. Another one here, potassium combined with chlorine gas gives us KCl. So in a synthesis reaction, we have two reactants combining to form one larger or complex product. For this to occur, the reactants must first collide, break existing bonds between their atoms and form new bonds. The chemical equation for the synthesis has this general pattern. Okay? So with this first one here, I looked at a metal combining with a non-metal compound and making an ionic compound. You almost think of it like this. If you think of a heterosexual relationship, guy, girl come together to make a couple. There we go, join together. If we look at the flip side, so examples of this, we can use the example of the burning magnesium in a sparkler to illustrate how to predict the product of a synthesis reaction. The reactants in this case are magnesium and oxygen. Oxygen is necessary for most combustion reactions to occur. Write the balancing chemical equation for this. So if we have magnesium combined with oxygen, and of course oxygen, oh yes, the old Hofbrinkel set. So oxygen is in that Hofbrinkel group, so it exists as O2. So they'll come together to make a compound. So of course what we have to look for there is the ionic charges on each one of those. So magnesium, of course, Mg2+, and oxygen is right over here. Where are we at? Oxide, O2 negative. So when we have magnesium coming together with oxide, so 2 plus, 2 minus, so they come together perfectly in a 1-to-1 ratio. One magnesium combines easily with one oxide. And of course here we have one magnesium, but here we have two oxygens, one oxygen. So we would have to put a coefficient in front of there, giving us two oxygens. But that's going to give me two magnesiums. So I'd have to place a 2 in front of there. All right. What about another one here? Calcium and bromine coming together. So calcium and bromine. And oh yes, bromine is part of the Hofbrinkel group, so it exists as that. And when they come together, calcium, of course, if you look back at that sheet, calcium ion is 2 plus, bromide ion is 1 minus. So yes, we'd have to have two of those bromide ions to balance that one calcium. So one calcium combines with two bromides. So CaBr2, and oh, that makes it balanced as well. Next one, aluminum and oxygen. So aluminum in the presence of oxygen, and yes, oxygen is a Hofbrinkel. So they come together to make aluminum oxide. Aluminum, if we look up that on the chart, of course, it is Al3+. Oxide's 2 negative. So yes, this doesn't work, but if we have a second aluminum and 3 oxides, that's going to give me a total of 6 negatives to be balanced with 6 positives. So 2 aluminums, 3 oxides. 2 aluminums, 3 oxides. And you can see through the paper here. So if I look here, now 2 oxygens, 3 oxygens. Now I'm going to have an issue here with odd numbers. So again, the best thing to do is to put a 2 in front of there. That's going to give me 4 Als and 6 Os. And over on the left-hand side, I have 1 and 2. So to get the proper number of aluminums, 4. And to get the proper number of oxides, if I put a 3 there, that'll give me 6. So there's the balance formula for aluminum coming together with oxygen, making aluminum oxide overall. So if you look at the next page, all reactions that we considered so far involve metals reacting with non-metals to form ionic compounds. So metals and non-metals. Some reactions involve only non-metals though. So synthesis reactions of non-metals, we can apply that same pattern using it for non-metals. So hydrogen is usually a group 1 element. Most group 1 elements form ionic compounds when they bond with other elements. Hydrogen, however, usually forms molecular compounds. Molecular compounds are made up of atoms, not ions. However, ionic charges are still useful in predicting the products of a synthesis reaction. So for example, if we have hydrogen and chlorine, so of course they're both Hofbrinkels, so that's why they exist as H2 and Cl2. If we apply the ionic charges here, so if I have that, we know it's going to be HCl. And H, of course, is +1, chlorine is -1, so they come together to form HCl. And yeah, if we're balancing that, 2 hydrogens, 2 chlorines, so I have to put a 2 in front of there to get my 2 HCls. The reaction between hydrogen also has the following pattern of synthesis. So again, oxygen here, H2 and O2 giving us, now in this case, we know it's going to be H2O because hydrogen, if I use charges, so yes, we're going to have 2 hydrogens for every 1 oxygen. So hydrogen gas plus hydrogen and oxygen gives us water. And then, of course, just balance that out using those coefficients there. The reaction of hydrogen with oxygen releases a great deal of energy as well as water. This reaction has the potential to be an important source of green energy. In fact, a fleet of hydrogen buses was used in Vancouver during the 2010 Winter Olympics. So right there you can see, powered by hydrogen. However, since hydrogen does not occur naturally, it has to be extracted from something else that contains hydrogen. And of course, that requires energy. Therefore, to consider hydrogen fuel truly green, we need to be able to generate it from environmentally friendly raw materials using renewable energy sources. Water would be a suitable raw material. Solar power could be another one. A little bit about synthesis reactions not involving hydrogen. So the products of synthesis reactions of non-metals other than hydrogen are very difficult to predict, and they depend upon what we have for reactants. The products of these reactions often depend upon the conditions. For example, 2 products are possible for the reaction with carbon and oxygen. So let's take a look. Carbon and oxygen, carbon and oxide. We could either make CO2 or CO. So it depends upon the availability of carbon and oxygen. In these cases, the only way you can test it is to, conduct a chemical test to see if we have CO2 gas or carbon monoxide gas. Other compounds, so far we've only looked at elements coming together to form compounds, but we could have compounds coming together with other compounds. So for example, if we have water and CO2, so there we have not individual elements, but actual compounds, and it forms carbonic acid, a more complex compound. So we could use an indicator to indicate what we have being formed there. So we have carbon dioxide reacts with water containing bromothymol blue. That's one indicator we could use. Air contains a small percentage of carbon dioxide. Whenever water is in contact with the air, some of that carbon dioxide dissolves in the water and reacts to produce carbonic acid, just from this previous equation right here. So carbon dioxide reacting with water to make carbonic acid. So that sometimes happens if we have good old CO2 in the atmosphere. Okay? So if you have CO2, it could react with that. It increases, so the recent increase in carbon dioxide in the atmosphere has produced a significant increase in the acidity of the world's ocean. This increased acidity could have devastating effects. So for example, coral right here in the sea is made of calcium carbonate. The calcium carbonate reacts with the acid in the ocean to produce soluble compounds. What happens is that coral reefs gradually dissolve and crumble. Sulfur trioxide is another compound that is affecting the environment because of this synthesis reaction. So sulfur trioxide, it's produced during the combustion of fossil fuels, and it can also react with water to make sulfuric acid. So the product of these previous two examples could be predicted simply by combining the two reactant formulas. Unfortunately, we can't always do that. It's not as easy as it seems sometimes. Some of these it is. If we have element and element, it makes a compound. Okay. So what I'll do is I'll stop the video there, and then we'll look at the reverse decomposition reactions.